Hi, my name is Andrzej Kaczorowski. I'm the chief scientist and co-founder of VividQ, which is a frontier tech company specialized in holographic display. I hold pretty multidisciplinary background. I come from physics, computer science, engineering. Actually, during my PhD, which I completed at the University of Cambridge, I managed to achieve real-time holographic projection on completely off-the-shelf GPUs, which was quite a nice result. And later on, we extended that work, and I led the proof of principle that eventually actually led to the co-founding of VividQ. Initially, I started as a hands-on person, so I developed the first code. I put together first holographic projectors, but quickly we saw the need of a dedicated hardware division, which I then built up as and led for 3 years as chief technology officer. And then I became chief scientist, so I branched off to lead more research-focused projects. Today, I will tell you a little bit about what we do, a little bit about computer-generated holography, and how VividQ applies that to the field of augmented reality. So I think everybody agrees that augmented reality has huge potential, and it's getting everybody quite excited. So this is a quote from Tim Cook, CEO of Apple, who says that in a couple of years, in 5-10 years time, we will look back at today, and we will not be able to imagine how we actually lived without augmented reality. This is how much this field actually promised to revolutionize human lives. And we're all here because of AR. So let me very quickly give you an introduction how we see augmented reality from the technology perspective. So when I mean augmented reality, I should probably specify, I mean actually head-mounted see-through augmented reality smart glasses, headsets, head-mounted displays. And in order to understand the field thoroughly, we need to look at it from different angles. So one, you could think about the display principle, how the display actually achieves three-dimensionality, whether it does at all. You could also look at the underlying display principle and figure out the bunch of trade-offs that are happening there. Or you could focus on the image delivery system, how image actually gets transported into your eye. So depending at which angle you look, you gain new insights. So stereoscopy is a very old technology. In fact, it's been known for more than a century, and it relies on showing two flat images to two eyes, and then relies on your brain doing a little bit of work to figure out three-dimensionality based on that. The only approach on the market which goes beyond stereoscopy is Magic Leap. And Magic Leap does that purely in hardware by stacking lots of waveguides. So we have 3 waveguides, 1 for each color for a close plane and 3 waveguides for a far plane. Then when it comes to the underlying display technology, we have quite a few of those, particularly LCOS and DLP. They perform quite well when it comes to light through output. And OLED, while it's really spectacular for mobile phones and leads to very high contrast, doesn't do particularly well in terms of brightness. And now laser beam scanning has been introduced by the second HoloLens. And it also was previously in Northfocus before they were acquired by Google. The third point, image delivery system. Here, waveguide is the most established solution. It's simply very convenient, but actually is very lossy. While Prism and Birdbath are high quality, and in particular, Prism was pioneered by Google Glass, also used in Epson, Bed Bath is used in Unreal and Lenovo. So there are quite a lot of nuances, and actually, it's difficult to sometimes make sense of it all. But all of those technologies for now share one common factor, which is none of those are yet a mass consumer product, and that's eventually where we as an industry have to get to. So there is a lot of research. What are the factors influencing mass consumer adoption? And about a year ago, we actually compiled all those sources and released a paper at SPIE AR/VR/MR in San Francisco. So 3 biggest hurdles, according to the research we compiled, is brightness, size and weight, and depth perception. Brightness, well, we want to be wearing our displays outdoors, and comes out that it's not so straightforward for some technologies to achieve outdoor brightness. Size and weight, nobody wants to wear a brick on our faces. And that influences how we feel about those displays. That influences how displays are perceived by normal people on the street. And the last point, which is quite important, is that augmented and mixed reality particularly deals with interaction and objects at arm's length, at which point depth perception actually becomes a crucial factor. So let me pause for a second and move over to holography. Holography was computer-generated holography was invented shortly after the invention of the laser in 1960s, and a lot of good work was done initially at the university. So MIT pioneered in acousto-optic modulators, while Cambridge focused more on liquid crystalline silicon spatial light modulators. One approach which requires mentioning is kinetic. So that was well ahead of its time, and they achieved a very high quality image by simply tiling lower resolution holograms next to one another. It was spectacular, well ahead of its time, but from what I know, it ran into technical difficulties and the project had to be discontinued. What makes me very happy is that big players like NVIDIA Research and Microsoft have joined the game of contributing to the field of holography. So 2017 saw 2 very good publications from those 2 players. And 2020 and 2021 saw an explosion of variety of good pieces of research with Stanford and MIT looking into combining holography with neural networks. Of course, VividQ has been working very hard on both the real-time performance of algorithms as well as image quality, and we have been working on getting holography to the state where it can be released to the consumer market, and so demos are coming in 2020. Stay tuned. So what can holography do for augmented reality? As I told you previously, we have identified 3 main factors. So brightness, size and weight, and depth perception. And let's look at how holography actually solves those. When it comes to brightness, holographic image can be as bright as the laser. So one interesting way to look at it is actually think of a hologram as a convolution. So you're essentially convolving your laser with a very, and I put it in inverted commas, a very controllable blur pattern, which actually leads to the 3-dimensional image. And I'm not saying that anybody would like to look into such display, but for instance, we have pupil replicating waveguides, which are excruciatingly lossy on the order of % or a fraction of a %. and holography can counteract for those losses. Size and weight here, our benefit is quite indirect. So holography offers you the ability to correct for your optical imperfections. And so you can accept certain degree of error at the design stage. And that means that you can simply design smaller, imperfect optical systems and correct for it on the software side. And that links me to the second point, that holography is actually a software-defined display or a computational display, which means that the properties are actually defined by the software rather than the hardware. And the last but not least point is the fact that holography offers you very natural three-dimensional viewing, which eliminates what is known within the industry as divergence accommodation conflict. We talked a little bit about holography, a little bit about AR, but now let me give you an introduction to VividQ, the company I co-founded, and how VividQ is advancing the science of CGH. First of all, we view that holography as the ultimate display technology. And in principle, any display could become holographic, could benefit from escaping a flat screen and going into the third dimension. But right now we are focusing on three main applications, and those are augmented reality wearables, head-up displays for cars, and gaming monitors. And of course, other applications will follow with time. And VividQ's vision is to become what Intel is to computers and what ARM is to mobile phones. We want to provide a technology stack, simply powering all those displays, making all those displays work. So let's look at how we actually got to this point. So we started at the University of Cambridge back in 2016, and we productized our software. We started developing an end-to-end software platform. And shortly after that, we realized that what we're proposing is actually a revolution of the display industry. So we went out and we formed very strong partnerships with a variety of players on the market who support the same vision and want to be a part of it and want to help us out. And right now we are working on a number of joint development projects leading eventually to mass manufacturing of holographic devices. So as I mentioned, we started from University of Cambridge, a photonics department, 6 people strong. Now we have grown to a very sizable company. It's 40 of us, of which 12 people hold PhD degrees and are solving the most fundamental problems. So we have maintained, over the years, we have maintained very strong relationships with the University of Cambridge via the CDT, Connected Electronic and Photonic Systems Center for Doctoral Training, between Cambridge and UCL, and also Center for Digital Entertainment. And actually, as a chief scientist, I lead that function, and I collaborate actively with those centers. So let's look at VividQ's innovation and where it lies. So when it comes to software, when we started this company, we realized that there were some key issues. For instance, in 2015, real-time holography was not something that you've heard of. And also there was no standard pipeline. And we noticed that particularly holographic optical engineers have to tendency of ignoring all the advancements of computer graphics that were being made. So we solved all of those problems, and we created a uniform pipeline that actually extracts the data from existing sources and takes you all the way to very high quality holographic images. So something that you may not know is that three-dimensional data has been in computers for a very long time. So any computer game inherently has something which is called depth buffer or Z buffer, which is simply the distance from the viewer to the closest object. And that data was not being consumed anywhere because we didn't have means of displaying it. So our pipeline linked to all the three-dimensional data sources and did all the heavy lifting when it comes to calculating holograms, and then made sure that whatever end device we are displaying our holograms on, that we optimize against those realistic devices. So let's look on the other side, and actually this will be the bulk of my talk. Are the hardware designs, hardware prototypes that we have developed over the years. We started quite small and modest. So that was the first headset prototype that we have built, simply because we needed something to demonstrate our technology at events, and we had about a month to do it. So that is something that we have built in-house. We used to joke that one day we bought a bike helmet, drilled some holes in the side, and said that, well, this is strictly speaking head mountable, and it relies on you having strong neck muscles. Very quickly we realized that we need something a little bit more sophisticated. So we arrived with this. And if you look at the previous picture and this one, you think that there is a massive difference, and there was when it comes to ergonomics and the fact that this headset was a lot more transportable. It didn't misalign so quickly. But actually, under the hood, there were the very same optical systems, same spatial light modulator and laser driver, and even optics had the same design principle. Looking at the optics, we are starting from the laser light, then expanding and collimating the beam, which then illuminates the spatial light modulator, which modulates the beam in a reflection mode. And then again, spatial light modulator is here on the top diagram. And then this arrangement of lenses actually forms a real image within that volume. And the folding mirror actually acts as a spatial filter. So instead of having an aperture, we simply have a mirror which only reflects the parts of the beam which are relevant to us. And that is then delivered to the eye with an eyepiece and a plate beam splitter combiner. When it comes to mechanics, we constructed back optics out of metal to make sure that it doesn't misalign, while the front optics was plastic, but it still behaved very well when it comes to optical performance. And everything is neatly packaged into the 3D printed shell. So yes, we traveled the world with that headset and gathered loads of feedback, and actually feedback both from the people who were receiving the demo as well as us giving the demo. Looking the reactions, seeing what are the problems with the demo experience, how we can improve it. So key pieces of feedback were the iBox is a little bit difficult to find. And actually we realized that human heads come in all shapes and sizes. And sometimes it's just not possible to position the headset in such a way to make the person see the image. Also, we got feedback on image quality, the compactness of the device. So we went back to the drawing board and arrived with this, which was our second prototype, showcased at SPIE AR/VR/MR in San Francisco at 2020. And you can see, first of all, it's binocular, but something that I'm very, very excited about is that the optical engine was greatly miniaturized, and it also had a number of features like IPD adjustment, and was a lot more sturdy. As I previously mentioned, Optical Engine was an absolute beauty. And in fact, you can see the relative size by looking how it compares to a dime. So again, we actually used the same laser diode, expanded, collimated, illuminated DSLM, and then at this point, we are forming the real image with focus. So within that volume, which actually is here on the base plate, we are capable of fully controlling the position and the focus of the beam. And what's fascinating me about this is that something that used to occupy the entire breadboard is now simply fitted above your eye. So right here, you can see the base plate rotated upside down, and you can see how the image goes onto the bed-bath combiner and gets delivered to the eye with all the components being annotated. And that really fitted very, very, very nicely in our hands and was really quite a spectacular achievement. Actually, while optics was very clever, equal amount of work went into the electronics and design. So packaging the driver boards was non-trivial, making sure that the flexi cables are folded properly, and the entire thing was user-friendly, was quite a challenge that I think we've done quite well. And also the IPD adjustment mechanism was quite advanced in order to provide us with that rigidity to then being able to position the eye box properly. Headset V2 was a great achievement, but there's one particular point of feedback that we received both actually on V1 and V2, and this actually boils down to the fundamental physics, and this is the field of view and eye box trade-off. So we always aimed in both of those devices, we aimed at field of view of about 30 degrees. But then the eye box, we had to shrink it down to about 2 millimeters in order to achieve that field of view. And you can, exchange one for the other. You can go for smaller field of view, bigger eye box, or you can go for bigger field of view and smaller eye box. And one common approach in the industry of extending the eye box is known as pupil replicating waveguides. And in fact, this picture is taken from the book of Bernard Kress, Architectures of Virtual Mixed and Augmented Reality. And you can see that if you attempted to actually image a three-dimensional image through the pupil replicating waveguides, what you would get in result would be a little bit rubbish, broken down, different scale. So it has been thought within the industry that imaging fully 3D images through a waveguide is impossible. Well, let me tell you one very exciting advancement that we made. We actually developed a method of imaging our computer-generated holograms through pupil replicating waveguides, giving you a full 3D experience. So please do get in touch with me if you would like to arrange a demo. Of course, we also released a white paper. If you would like to learn more, please head to our website, vividq.com, and download it. And I am also more than happy to answer more technical questions. So please do get in touch, ak@vividq.com or Andrzej Kaczorowski, and my LinkedIn is Dr. Andrzejka. So thank you so much for listening, and I'm waiting for the questions.